In this tutorial, we are going to learn about the stack and the stack pointer, what that is, and how that's going to help us solve the segmentation fault that we were having in our prior code for this series. So if you come from a high-level language background, then you'll know that a stack is just this big chunk of memory, and it's what's used in a lot of data structures problems. Well, similarly, here in assembly, we rely on that memory to save values so that they don't get lost. So if we wanted to preserve a particular register value or something, and we didn't really have an efficient way to do it without using the stack, then the stack would be something that comes in handy. So let's go ahead and continue with this. So, if you recall, registers are these particular parts of the CPU which we include and modify values, and we work as such. Similarly, in the stack, we have these addresses where we can store values, or we can store register values. So here I got in address 2000. There is no value there. Keep in mind these addresses here are not actually content. So I just wrote them there to show you that those are the particular addresses for each location on the stack. So these are memory addresses, and content would be stored in those addresses accordingly. So if we store some value, we have that. And keep in mind that the size of a register is 4 bytes, and each memory address here, so we have address 2000, each value, I should say, or each number that makes up the value of the memory address is 1 byte. So if that doesn't make sense, let me explain using this example. So we have address 2000 here, and then we have address 1996. This is subtracting 4 bytes from 2000 to 1996. So these memory address numbers, each address is 4 bytes. So if we're working with registers and integers specifically, then this is the representation to follow, because a register takes up 4 bytes of memory, and and integers also take up 4 bytes of memory, and we've been working with integers in this whole series so far. So all of this whole bar here at address 2000 can store 4 bytes of anything, whether it's a single integer or whether it's 4 characters, because a character takes up 1 byte. And then this is a new bar here, address 1996, which has 4 bytes. Again, store anything you want. It's just based on what you're trying to solve. Address 1992, again, 4 bytes, and so on. Keep in mind that this is actually not what the stack looks like. This is just a representation. So actually in reality, if I were to draw some lines here, so that I draw 1 line here, 1 line here, and 1 line here. So there would be 4 sections on this bar. That's because, like I said, each memory location is 1 byte. So there are actually 4 different locations here. But the reason why we're representing them as 1 bar is because we've been working with 4 bytes, so it's easier to think of it as one thing. If we were to get into using characters, then we'd have to draw this differently. But we're working with integers and we're working with registers, which are both 4 bytes, so each of these longer bars here is 4 bytes. So Here we have address 2000. If we were to split this up into 4 sections, it'd be 2000, 1999, 1998, 1997. Then here would be 1996, 1995, 43, 1992, and so on. So it's all 1 byte. But we're using that initial byte or that initial address number to represent that whole group of 4 bytes. The other thing is that notice that the addresses are decreasing as we go down on the stack. So we start at address 2000. Again, for, it's not, this is not specific to a particular computer, so it could be address anything. I just used 2000 for the sake of this example. So whatever address the stack starts at the address, and then the address decreases as it goes. So this is actually an inverted representation of the stack. So right here, what we have at the top here at address 2000, this is actually the bottom of the stack. And as we decrease in memory address, we are going up the stack. So that's why this right here, it says downward growing stack. This is actually specific to the ARM architecture. So for other assembly languages, it could be different. But for ARM, the convention is a downward growing stack. So at the bottom, you start at the highest memory address, and then as you go up the stack, your memory address decreases. I just drew it in an inverted manner so that it looks more consistent with what we're used to, that at the quote-unquote bottom, we have the lowest memory address, and then at the quote-unquote top, we have the highest memory address. But keep in mind, this is bottom, this is top. Next, we have some stack operations that you might be familiar with if you come from a high-level language, which are push and pop. Now, push is just, it pushes values into the stack. So I actually did this wrong here. Let me just quickly edit this. Sorry. So push, yeah, I put a parentheses there. Just should have been curly brace, open, close, curly brace, not open curly brace, close parentheses. So we have push, which just, based on the different values you have within the curly braces, it pushes those values within the stack. So notice here I pushed register 1, register 2. Now, keep in mind that it doesn't actually push the register itself into the stack. It pushes the value contained within the register into the stack. So if register 1 had the value 5, for example, or in our case, register 1 has the value 5. Register 2 might have something else. I think with our modulo case, the answer was 4, so it's going to have 4. We're not pushing the registers themselves into the stack. We're pushing the values of the that are within each register into the stack. And then similarly, pop, that's the reverse of push, as you guys might be familiar with if you've worked with the stack data structure. Pop just takes it out of the stack. So we push the values into the stack, and then we pop those values out of the stack. Once, like, so we push, like, in context of a real problem we're trying to solve, we push the values into the stack to save them so that when we tamper with these registers, the values are going to be modified, so the original values that we want to preserve, they don't get lost if we first push them into the stack. And then for pop, once we have, worked with the registers and such and accomplished everything else after the code, then we just pop the original values back into back into those registers. Okay, so like I said, we're not pushing the registers, we're pushing the registers contained values. So here I just put in some random values, so we got 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 9. Again, could be any integer. Like I said, an integer takes up 4 bytes of memory. So we push them into the stack as so. And then the stack, we have what's called the stack pointer, which is, it points at basically the top of the stack. So like I said, this is an inverted drawing. We have the bottom here at where, 1, 2, 3, 4, 5, 6, 7 is. And then we have the top at the very bottom, which is the lowest memory address of the stack. And here's the highest memory address. So we have so remember, as we're going quote unquote bottom in this inverted drawing, we're actually going to the top of the stack. And the stack pointer, its job is to point at the top of the stack. So this bottom is actually the top, and that's where the stack pointer is pointing at. Remember, when we're having a segmentation fault, it just means that we are tampering with the stack pointer unintentionally. So in order to understand why that's the case, we need to understand what the stack pointer is and what it does. So if the stack pointer is something that has been unknowingly tampered with, it means we have not used or we have not worked with the stack correctly. And if you guys remember from our previous videos, we have not actually worked with the stack at all, yet we tampered with the stack pointer. So that's something that can happen, and that's why it's important to learn how the stack works so that you can use it to your advantage to not get a segmentation fault. So let's jump into our code and see what's going wrong. So the two main things we have to deal with here are the push and the pop operations. Remember, the whole point of using the stack is so that we can save values that will otherwise get lost and then be able to bring them back. So what we need to do here is we need to push and then pop something. Remember, we're getting a segmentation fault because we're unintentionally tampering with the stack pointer. And keep in mind, we haven't even worked with the stack at all up to this point. So if we're getting a segmentation fault without using the stack, then the question is, how do we use the stack so that we don't get a segmentation fault? So I'm going to go ahead and actually copy paste some code I had from an older project because it's filled with comments. So there we go. So what I have here is I have, and keep in mind, 2 slashes work for comments, just like @ just like hash, just like semicolon. So what we're doing here is we're pushing something, and one thing I want to point out is that with the stack, or with the push command, the program reads right to left. So how we've been doing these move commands and this add command here, like move the value 19 into register 0, move the value 5 into register 1. It's all been a right to left reading. Similarly, with push, it's also a right to left reading. So whatever's in the curly brace separated by commas are individual values we want to push into the stack, and it reads right to left. So it first pushes LR, which stands for link register, and then it pushes FP, which is the frame pointer. So keep in mind that, remember, the stack pointer is always supposed to point to the top of the stack. So when we're pushing and popping values into the stack, the top of the stack is automatically getting modified, and therefore the stack pointer is automatically adjusting. So we don't have to manually do much with the stack pointer because that automatically adjusts. Now the reason why we're getting a segmentation fault is because it automatically adjusted in such a way that wasn't what we wanted. So when we push this, we push, keep in mind, all these are special purpose registers, FP and LR. We push 2 registers into the stack, or the values in 2 registers, so we automatically push 4 bytes, then 4 bytes, so 8 bytes of memory into the stack. So keep in mind this comment here says after every push the stack pointer goes down by 4 bytes in a high to low growing stack or downward growing stack. And then the stack pointer points to the last filled location in the stack memory or the top of the stack. So if there's nothing there, the stack pointer is not going to point to that place. So the stack pointer points to that last filled, that topmost location in the stack. So what we do is we need to update the value of the frame pointer, which was the second thing that we pushed into the stack. And what that does, it's going to go up to the base of the current function stack. So the current function we're in is main, and we need to go up to the base of the current function stack. So keep in mind, we first pushed LR, so that's at the bottom of the stack, and then FP is right above it. So if we update the value of the frame pointer by adding 4 bytes, then we're back at the bottom, because remember, at the bottom most is the higher address. So when we're there, then we go down, and when we go down, basically our frame pointer has been, I'm not going to use the word reset because it was never there to begin with, but we update the frame pointer and it's at that base where, the link register was pushed. Similarly, we need to do some popping. So once again, I'm going to copy the code from my older project just so it's faster and it has all the comments already. So let's go ahead and do that. Okay, there we go. So after we do all the work within the main function, do everything, all of this nasty business working with the registers, and then we need to basically remember that we were using the stack. Sorry, that wasn't part. So these 3 lines are the quote-unquote nasty business that we're doing with the within the main function once we preserved these values in the stack in these first 2 lines. And then we need to do the inverse of that, because with a push comes a pop and with an add comes a subtract. So we need to subtract 4 bytes from the frame pointer, and that's going to be the new value stored into the stack pointer. And the reason why we want to change the stack pointer, this is the one time we're manually updating the stack pointer. And the reason why is because we want to go down just past the saved callers registers. So in this case, what we want to do is we want to, when we work with the frame pointer and all of that, remember, we just updated the frame pointer to go to the base of the current function stack where, the link register was. And then what we do is we have to keep in mind the stack pointer was automatically adjusted. So we just need to update that value of the stack pointer to get it to just past the saved callers registers. So I'm going to go ahead and make a visualization of this so it's more clear when we're doing function calling and working with the stack. That's where the term caller and callee comes in. But for now, the caller saved some registers. So then when we're doing all this function calling, like with mod here, all these values are getting tampered with. So we want to save the original caller's registers. So once we do that, then we update the stack pointer. So we go back to where the caller was. We've been working with the callee mod, and then doing that, and then back to the caller, which is main. And then we need to do a pop, because with a push comes a pop, otherwise working with the stack is completely useless. So we pop the frame pointer, and then we don't pop the link register, we pop PC, or the program counter. So what this does is it restores the caller's frame pointer and then the return from the function. So with main, it might not be as significant per se, but when we're doing sequences and sequences of function calling, then then for each function, which is calling another function and is the callee of another function, that's where this comes in handy. So with main, which is the original caller that is not the callee, there isn't much to the story. But when we work with mod, or if we had at least 3 functions in this problem, it might have been more obvious. But we only have 2 functions, so main is the only caller and mod is the only callee. But if we had some other function, I don't know, function A, for example, and we were calling that in mod.s, then mod is caller for that function, func A, and it's the callee in the main function because we just called it here. So when we're working with these chains, I should say, we want to be sure that we're saving the caller's original values as well as acknowledging that the callee brought in some new values. So that's the whole idea of function calls. So that's a very big thing when we're working with assembler programs. So that's basically it. Here's my visualization of what I mean when we do the function calling and have to use the stack and frame pointer and stack pointer and all that stuff accordingly. So we have here main, which is the original caller. So there's, with the push and pop, there's not much significance. But then we call a function, blfunc1, which is our mod in this case. So then we call func1, and then with that, we do all of that, this, that, and then we call another function, func2. So func1 is in the middle here. Func1 calls another function called func2, and it's the callee of another function called main. So then func2 gets called, does all of that. Remember, when you call a function, its return value is going to be in register 0. So you get a value, register 0 is tampered with, and this is the callee's register 0, which then becomes the caller of func1's register 0. Then you do all of that, then you get a new value of register 0. That's the callee's register 0 because the callee now is func1, and then the caller is func2, is main. So then that gets updated when you call func1 in main, and the program responds accordingly. So when we're doing more and more complex function calling like this for more complex programs, it's difficult to do all this function calling and keep track of which registers are being modified. So that's why we use the stack. So, and that's why we do that pushing and popping, and we are concerned with what the original caller and then the callee is, because here we have main being the caller, and then the callee is func1, which then is the caller of func2, and this complexity is the reason why we have to use the stack. Now, the last thing we have to do is we just need to add a few minor details so that in the terminal we can confirm that the program actually works. So the first thing I want to do here is, if you guys come from a C background, you'll know that oftentimes we do a return 0 in a C function to indicate that the execution of the function was successful. So what I'm going to do here is I'm going to move into register 0, because that's where all the return values are, the value 0. And then to add a comment, we can really use either syntax, @ or 2 slashes. I'm just going to start using 2 slashes because it's closer to most other languages' common syntax. So I'm going to say save return value of main, or not save return value of main, more like return 0 to denote success. There, that's a better comment. And then obviously we know that in mod the return value goes into register 0, and we don't want to interfere with that. So the next thing we need to do is we need to save into, we can use any register. I just typically use register 5 to save function return values. the value of register 0 we're going to save into register 5. So save return value of mod function. Now, one final thing I want to add, this isn't exactly necessary, but it is a validation that the program works, is we need to, as I'm going to add a print statement. So what I'm going to do here in line 5, just making sure you guys can see it, yes. I'm going to add a label and I'm going to call it success. And .ASCII-Z. And then we're going to say mod has been successfully calculated and stored. And then I'm going to do a \n so that it's a new line, or a new line is created afterward. And now here, just like we've been doing with print statements and other functions, LDR R0, comma, space, equals, and the name of the label, which is success. And then call the function printf bl printf. Okay, so let's just, yeah, this should be good. So let's go ahead and test this out in the terminal. Alright, so let's go ahead and test this out. So I'm just going to quickly compile here. Cool, no errors, no warnings, and then ./test. And you can see with that print statement, the program did indeed complete the execution, but obviously this doesn't tell us whether the mod value was in the correct register or not. So for that, we have to go to GDB. And again, if you want GDB to work, you need to put the .g in front of the or not .g, the -g in front of the -o. So let's do that. And then I'm going to put a breakpoint. So I'm actually not going to put a breakpoint at mod. I'm going to put a breakpoint at the next line, which is our LDR. So in my case, it's line 22. So b main.s 22, which is the LDR R0, comma, space, equals success. So I'm going to put a breakpoint there because this is just after mod has executed. So we're just going to take a big leap here and see if the correct values are in the correct registers. So, and the line that has just been executed is line 20, which is move R5, or move the value in register 0 into R5. So basically the value 4 should be in register 5. So let's do an IR. Oh, sorry, we didn't run it. So R for run. And it stops at that breakpoint. So now IR. You can see indeed from mod, register 0 has 4, which was calculated and put into register 2 at first. And then to save the value, we put the mod value 4 into register 5. So it works.